An essential element of quantum mechanics is the concept of quantum mechanical entanglement. This is a type of correlation between the physical states that is more powerful than and not possible to describe within the confines of classical mechanics. Engineering of entanglement enables us to solve problems that are otherwise not possible to solve.
Building large quantum computer is building instruments that allow it to peer into the unknown, to new science, to new insights into how the universe works.
Quantum computers can solve these problems that have been known for a long time, but don't have good solutions on classical computing hardware, and really change the world.
The Quantum Moonshot project is focused on building a quantum computer on a chip. It has to be a scalable, fault-tolerant computer, and that is our objective. This is an extremely challenging task.
What sets the Quantum Moonshot apart is that it was founded on a principle to go big or go home. What is the essential problem that, if solved, will allow for scalable quantum information processing?
We like to think of the Quantum Moonshot as unique, both scientifically and organizationally. We have approximately 40 scientists, leading scientists at MITRE, MIT, Sandia National Laboratory, the University of Arizona, the Danish Technical University in Copenhagen, and Amherst. Our laboratory is quite large as a result of this, and we have the chip fabrication capabilities at Sandia.
We use an architecture that's very different than all of the other approaches. We're trying to use the magical properties of diamond, which can form a perfectly isolated atom inside of the diamond.
In a quantum computer, a quantum bit, or a qubit, is the physical state of a quantum mechanical system that has an action. It is very, very small. The action of a physical system has units of angular momentum.
The angular momentum in particular can be used to store quantum information. We actually use the fact that diamond can form these little defect complexes that behave for all intents and purposes like an atom, except that that atom is trapped inside of the diamond. Those artificial atoms in the diamond, they can both store quantum information as spins, and they can emit entangled information essentially as part of a photon and part of a spin. So there's a qubit that is essentially a hybrid of both an electron spin and a photon. Those that allow us to interact the spin qubits, which are stationary, sitting in isolated little pieces of diamond, but they can interact with each other through those photons and become themselves entangled.
When you have these small atom-like atomic systems, we can pack them closely and still address individual ones as necessary due to slight differences in the crystal. Basically, they're like little cell phones that dial into different frequencies that we can talk to.
You can build up this very large entangled state of spins in the diamond, in these color centers, these artificial atoms in the diamond. And then just making measurements on that large entangled state can drive a quantum computation.
So the advantage of our solid-state quantum bits is they're extremely stable and are long-lived. And they give us a stability that enables us to use these states as memories, quantum memories. It's also the case that these defects give us a natural spin-photon coupling, which allows the quantum information in the defects to be transferred into the photons and vice versa. And the photons then carry on their backs quantum information as they propagate around the chip, and in this way enable intrinsic scalability. And this is a key to our approach. We will have the ability in a scalable design to engineer as many qubits as are required. And for many problems, this will be millions or millions and millions and millions of qubits. And our approach, making use of photons, is intrinsically naturally scalable.
We use the same tools and techniques and materials to manufacture the silicon-based microelectronics that are in your phones and smartwatches and computers to make these photonic circuits, essentially, that guide light and also control the properties of these diamond chunks that are sitting on the surface of the microchip. And so that's what really gives us the scalability. And we've forced ourselves from the beginning to stay within that manufacturing paradigm of CMOS microelectronics to be able to build our devices, because we are exclusively focused on building something that is in the end scalable.
Make it into a device that I can give somebody. Put it out in the field, put it on a helicopter. And these are the things that are happening here in the TJ Artist Lab. And I love that my team is costed all around this lab, because every morning you're reminded not just to do science, to apply it, to try to make the world better.
Since the moonshot began, we have now approximately 50 published papers in peer-reviewed journals. We have approximately 15 patents in development. The team is dedicated. Every single member of the team feels that this is fundamental and important work. Quantum computers will pose significant opportunities for improving the experience of life of human beings, and we are dedicating ourselves fully to this work.